Buenas tardes a todos. Daremos inicio a la sesión número 10 del ciclo de conferencias en geodinámica del profesor Peter Molnar. Disfrútenla, por favor. Thank you, Peter. Go ahead.
Well, thank you, Hector. So today I'm going to talk about the mantle, how the mantle is involved, and mostly in terms of what we call Rayleigh-Taylor instability. And I will describe this, I hope, in a way that's clear. Just to put this in a framework, I want to look at the Alps and in particular the mantle structure under the Alps. So that the green is low, the white is high terrain. This is the Italian peninsula. Venice would be over here, and this is the Rhone River. And if one looks at the mantle, now 150 kilometers or 210 kilometers, the blue is showing high P-wave speeds. So P-wave speeds 4 to 5% higher than normal. And this is a large amount. In tomography often deals only with 2% or so. So 4 is big. And these big high speed zones under parts of the Alps, at 210 you see 3 of these, but at 150 you see only 2. But these are on top of one another. And the standard interpretation is with subduction. So here's a map, again, showing the 150 kilometer, the 2 blue areas. This profile A over here, the high-speed zone is below 150 kilometers, and they show it dipping to the southeast, and maybe it does. Then profile B, going through this one, well, they claim it dips to the southeast again, maybe. And then the profile C over here, well, they're coloring that blue, but they're showing it dipping to the southwest. Maybe it does. Maybe that's the right interpretation. But I look at these as essentially blobs of mantle lithosphere sinking into the asthenosphere, just sinking straight down. That's the way they look to me. And so my image is much more like this. This is a numerical calculation by Lorenzi and Hausmann, where if you thicken a little bit of a layer that's dense and you thin it a little bit, the dense part sinks and goes down. And this is what I think one is seeing under the Alps, not subduction, but these blobs that are sinking. And this is a Rayleigh-Taylor instability. Now, this is just introduction, another example. If you thicken crust, if you have normal crust with a normal geotherm, the temperature increases with depth. So depth going down, temperature going up. Through the normal, it's over here. If you thicken the crust in mantle lithosphere, you stretch everything vertically. And so then at this depth, not suddenly, but when you've thickened, you have low temperatures. You've taken the geotherm and stretched it downward. So all the temperatures are lower than before. But we know widespread Barrovian metamorphism that occurs in orogenic belts where we've had high temperatures in the lower crust. How would one get that? Well, I would argue you get that by removing the mantle lithosphere from underneath here. So the simple cartoon sequence that I'm imagining that I will then present in terms of Rayleigh-Taylor instability is if you thicken crust and you thicken mantle lithosphere, you wind up with thick crust, a crustal root, but also with dense mantle lithosphere. This is higher density than the surroundings, and so it's unstable. It wants to sink. And if it sinks and goes away, so the light blue suggesting that this mantle lithosphere here has been removed, you take a load off the bottom of the lithosphere, the surface goes up, but you also thin that mantle lithosphere. You wind up with a thin layer in here that's hot, and you wind up with extension. Extension eventually develops within this region. So this simple image I'm going to develop using what we call Rayleigh-Taylor instability. And that occurs when there's a heavy layer, a dense layer overlying a lighter one. And so what's drawn here, this is a numerical calculation just for cartoon's sake. If you have a layer, the red defining the layer, it goes out to infinity, and you perturb it a little bit, thicken it here, thin it here, thicken it here, thin it, thicken it, and thin it. The thick areas, because they're more dense than the surrounding material, will sink, and they will go down, and that's what's happening. The line here is the bottom of this layer which we would think of as lithosphere, it sinks and it goes down. And as it sinks, it accelerates. You can see that a minuscule deformation at this non-dimensional time of 0.4, a little bit more at 0.8, more at 1.2, and then it goes very, very fast. This non-dimensional time, I'll use this, but I'll probably use different numbers. And so this will change as we go along. So the Rayleigh-Taylor instability, a heavy layer over a lighter one. And the first thing I want to look at is linear stability. This is the growth of infinitesimal perturbations to the density structure, what I just showed you in the previous slide. So this is a blow up of one part of this. You can imagine you have a layer, but this layer goes out to infinity to the right, out to infinity to the left, and it's perturbed with a harmonic sinusoidal variation, a little bit thicker here, a little bit thinner here. And what we can determine is that the growth, if this is simple Newtonian viscosity, we can determine that the growth is exponential. The distance from the amount of thickening of the layer, the bottom here going down to however depth, this z of t grows exponentially. Q is called the growth rate, and Q is proportional to the density difference. This is obvious, I think. The denser this layer is, more dense than the underlying layer by delta rho, the faster it will grow. The faster, the growth will depend on gravity, because gravity is pulling it down. If you put it on Jupiter, it grows faster than if you put it on the moon. It'll depend on the thickness of the layer. This is maybe a little bit less obvious, but obviously the thicker the layer, the more potential energy is stored, the more dense material you have. So the growth rate goes up, and then the growth rate is inversely proportional to the viscosity. Viscosity would go down here in the denominator. And that's obvious, I think, because a more viscous layer will deform more slowly, it will grow more slowly, and so Q will be smaller for a large viscosity. And so I would argue that common sense gets you this simple relationship, the proportionality to the density, the gravity, thickness, and inversely to the viscosity. But then there's lots of other parameters that can go into this. K, wave number, that's like the wavelength, variations in viscosity. There's a whole lot that can be different, and it takes 20 pages of algebra to solve and get this value of Q prime. I'm not going to take you through that. The important part is the common sense, and what that value is, I'll show you different values, but we won't go through details. So just in simple calculations, if you plot the logarithm of the depth, z, or the logarithm of the speed with which the blob is sinking against time, because this is an exponential, you'll get a straight line. And these plots are showing you calculations that we've made. Eventually you deviate, eventually the growth is not exponential, it's actually super exponential. But the straight lines imply exponential growth. And let's just put some simple numbers in. Suppose the layer is warmer by 300 degrees C than normal. You know, the mantle, the asthenosphere is 1300 degrees C, so this isn't that big. Then the density anomaly associated with that is the density of the background times the coefficient of thermal expansion times the temperature difference. And you put numbers into that, density, coefficient of thermal expansion, temperature difference. 30 kilograms per meter cubed would be the value one would put in here. Gravity is 9.8, and let's let the thickness be 100 kilometers, h 100 kilometers. Let's just let Q prime be approximately 1 for the sake of argument. And a viscosity that's not very viscous, it's not as viscous as under a shield, but viscosity that's reasonable, 10 to the 21 Pascal seconds. If you put all of those numbers in and write this as 1 over Q, so 30 is the temperature, is the density difference, 9.8 is gravity, 10 to the 5th is 100 kilometers, and so forth, you get 1 over Q as 2.15 million years. That means the growth would be a factor of E folding 2.7 times in about 2 million years. And therefore, if you go 10 million years, you have a growth of E to the 5th, that's 148 times, so a 5% perturbation grows 750% in 10 million years. The point is that this can be fast. 5% perturbation to 750% in 10 million years, this can be very fast. Now, I should tell you that I picked some numbers that made this look better than maybe it should, but let's not worry about that. Okay, I want to take an example of how we can look first at simply the linear stability. And this is looking along California, the Sierra Nevada mountain range in here, the Central Valley. So Los Angeles down here, San Francisco's over here. Looking along a line like this, there is a high-speed region. The blue is showing P-wave speeds that are 5–6% higher than normal. Two blue regions, one called the Isabella anomaly here, lying under this region, one called the Redding anomaly, this end and up in here. And they're about 500 kilometers apart, and I'll get to that in a second. Okay, so to solve these problems mathematically, we need boundary conditions, and one needs a viscosity structure. I put some simple numbers in before with a simple structure, but boundary conditions come in two simple ways. Free slip, you let the top of the layer move freely with no resistance, or no slip on the top at all. These are the two extremes. And then one can have viscosity decrease with depth. A simple way would be over some layer H, it's a certain value, and then it's a smaller value by R, or it could be a larger value by R, down at some other depth, so we have this two-layered situation. Or one could imagine viscosity decreasing with depth exponentially, varying with a constant that depends on L, Z minus H, because that's this depth here, Z equals 0 is at the top. So if one puts some numbers or does the mathematics, one gets a plot like this, where this is the dimensionless growth rate. Remember this, you multiply by all those other constants that include viscosity and density. As a function of wave number is inversely related to wavelength. The so the wavelength is 2 pi divided by the wave number. And for a value of R that's very large, this means that I did this wrong. This means that there's essentially no viscosity in the layer underneath. One gets a curve that looks like that, and you can see when you go to infinite, when the wave number goes to infinity, therefore the wavelength goes to 0, or the wave number goes to 0, and therefore the wavelength goes to infinity. These both go to 0, and the maximum growth rate is around 2. Where 2 means K prime equal 2 means that the wavelength is 2 pi times the thickness of the layer divided by 2.12. The wavelength is 2 pi divided by the wave number. And so this is easily remembered. The wavelength of the most rapidly growing instability is about 3 times the thickness of the layer. So if the layer is 10 kilometers, we'd expect 30 kilometers. If the thickness of the layer were 100 kilometers, we'd expect a wavelength of 300 kilometers. Well, if we change the boundary conditions, what I just showed you was a rigid top and with an inviscid, no viscosity substratum. And here you can see the maximum is around 2.12 in here. If you let the top be free, so it slides freely and there's no viscosity underneath, not only is growth faster, but also the maximum growth is at infinite wavelength. It goes as fast as it can. And so you get, doing these calculations, 3 not surprising results. Growth with a free top is faster than with a rigid top. Well, a free top means it's not resisted as much, so it should grow faster. The fastest growth occurs at a longer wavelength with a free top. Well, that makes sense because, again, it's not resisted. It's free to spread out and go over a longer distance. And then a viscous substratum will reduce the growth rates and shift to longer wavelengths. And that's what happens here. If you still have a free top in these cases, but here you let the substratum be viscous, well, this slows everything down and it makes you peak at some wave number, which is a smaller wave number, a longer wavelength than if you had a rigid top, but it's still not, the maximum growth rate is not at infinite wavelength or 0 wave number. So if we go back to the Sierra Nevada, and we have these 2 blobs that are sinking, the distance between them we could see as a wavelength. 500 kilometers would be the wavelength we would use. And if we say that's the wavelength, and we assume this relationship that the wavelength is 3 times the thickness of the layer, we get a rather thick layer, 167 kilometers. 167 kilometers would be here. We don't have a layer that's that thick. This is too thick. So something is wrong. Well, let's go back to this. If we put a wavelength of 500 kilometers and a thickness of 100 kilometers for a typical lithosphere, we don't get K prime equals 2. We don't get this. We get K prime is equal to approximately 1, a little bit larger than 1, but out in this area. And this is what we might expect if we had a free top and a viscous substratum. Another way to see this, if we have unstable mantle lithosphere that's capped on top neither by a rigid no-slip boundary condition, as we assume for one of those curves, nor by a stress-free slip boundary condition, that's this curve. We have neither of those, but if imagine we have a weak lower crust, so we can have shear occur at low stress with a weak lower crust, then the top boundary condition on our mantle, the mantle lithosphere might behave more like a free than a rigid top, but not like a perfectly free top. And the maximum growth rate then will be controlled by the viscosity of the substratum. So if we put some numbers in, make some calculations, these are calculations where L is the e-folding dimension, how fast viscosity decreases with depth in an exponentially decreased lithospheric thickness. And you can see we've moved away from the case where the maximum growth rate is a wave number of 2 towards smaller values that are in the range of 1 or even smaller. So in this case, we have a layer with a thickness h, but with a stress-free top surface decreasing exponentially. That's essentially the case that we would imagine in the Sierra Nevada. The top is behaving rigidly, but it's got a weak layer at the bottom and then exponentially decaying viscosity below. And so we go back to this case and we can explain the longer wavelength, the longer distance between these two pieces because of the top boundary condition. Okay, I'm going to change directions. I have 3 or 4 different parts of this presentation, and I hope each will be more interesting than the previous. But what happens if we have a crustal layer? Well, imagine if you have a layer, crust, that's low density, so we'll treat this as crust, overlying a more dense layer, we'll treat this as mantle lithosphere, and you displace this horizontally. So we move this boundary here to the right over to here, and we allow thickening only over on this side. So the top boundary moves rigidly to the right until a position approximately here. So we thicken on that side, but we have 2 layers. And so what happens when we do this? We can imagine a bunch of situations. And for me, there was a surprise when we did this, because for different parameters, different densities, and these are dimensionless numbers. I'll discuss these in a minute, but don't worry about these for now. But different densities, different viscosities of the crust, treating the crust as viscous, and different thicknesses. Sometimes when we do this, we have sinking of the cold blob of heavy, dense material right where we thicken it, and we pull the crust down. But sometimes we have thickening not at the center in here, but off to the edge, on the far away from where we're undergoing the shortening. So the shortening is up in this region, but the thickening is off to the side. And sometimes, again, different parameters give you different conditions with thickening off to the side. And remember, this is just half of what we're doing. Imagine there's another piece, a mirror image over here to the right, where we have the same process going on. I rearranged my slides, so this is a little confusing, sorry. So if imagine you have this case with a mirror image, then in this case you would have 2 downwellings, a pair of them, a downwelling here and a downwelling on this side, whereas in this case you would have only a single downwelling. And we ask the question, what are the conditions that give us paired downwellings, and what are the conditions that give us single downwellings? And the crust plays a crucial role in this. So this is now a plot where we made many calculations, and this is a plot of some dimensionless numbers, but the black symbols show you paired downwellings. The open symbols show you the single downwelling case. So let's take this axis. This is a non-dimensional viscosity. the ratio of the crustal viscosity, the strength of the crust, to the viscosity of the mantle lithosphere. And you can see if this number is large, then you move to the right, single downwellings are favored. But if the crust is very low viscosity, you move into this region and paired downwellings are more common. Let's look at this axis. Let's start with M. M prime is the ratio of crustal thickness to the entire lithospheric thickness. So M ranges from 0, no crust, to 1, which would be entirely crust, no mantle lithosphere. And as M becomes bigger, it means we have more crust than mantle lithosphere. And when you increase M is M to the 4th power in this, in fact, as M gets larger, you get paired downwellings. When you have small m, you have a single downwelling. And the same is true, not quite so simply, with density. We have a dimensionless density, the difference between density of asthenosphere and crust divided by the difference between mantle lithosphere and asthenosphere. Mantle lithosphere is more dense than asthenosphere. Asthenosphere is more dense than crust, but this number is larger, yet the value of this number depends mostly on the density of the crust. So if the crust is dense, this number is large, you subtract it, this number is small. If you have dense crust, you're down here because we're raising that power to the 6th power, that's essentially 1. If the crust is very buoyant, low density, then this numerator is large, the whole number is large, you're up here. So the point is that if you have low density crust, you have paired downwellings. If you have high density crust, you have a single downwelling. And we worked out some theory for this. The theory predicted this black line. The observations are clearly showing it doesn't quite fit. It's more like this dashed line. I won't go through the theory, but I'll come back to that. But the point is, for some combinations of density ratios, viscosity ratios, and ratios of thickness of the crust to the entire lithosphere, perturbation to unstable mantle lithosphere grow not where shortening is forced, but adjacent to it. We have this paired downwellings as we have in this particular case. So how does this work? We imagine the very simple situation that gravity is acting on this dense mantle lithosphere and it pulls it down. And where it pulls it down, it drags the moho with it. This is downwelling. It's pulling the crust. The crust, of course, is less dense than the mantle lithosphere or the asthenosphere. This is pulled down. Simultaneously, gravity acting on the negative buoyancy of the crust. The crust is less dense than the mantle lithosphere. So when you pull it down, gravity is tending you to pull it back up. Gravity wants to pull the moho up. And the question is, who wins? In this particular picture shown here, the mantle lithosphere wins. The sinking of the mantle lithosphere pulls the crust down. But that's not always the case. So taking this a little further, we have two interfaces. We have a crust-mantle interface and a lithosphere-asthenosphere interface. And so we have two growth rates to the perturbations. If we perturb the depths of these interfaces, they'll be disturbed and there'll be a response. It's a viscous process, and they will grow, though one of them will grow negatively. The lithosphere-asthenosphere boundary is unstable. The lithosphere, the mantle lithosphere, is more dense than the asthenosphere, so a perturbation to its thickness will grow, and hence the growth rate is positive. But the crust-mantle boundary is stable. If you thicken the crust, it has the tendency to go back to normal thickness. If you thin it, it has the tendency to thin. So perturbations to it will decay, and hence the growth rate is negative. And ordinarily, decaying perturbations with negative growth weights die away. They don't grow. We don't have to worry about them. They disappear. But in this case, the horizontal is shortening, is thickening both layers. It's causing the crust to thicken against the gravity acting on it. It's causing the mantle lithosphere to sink, which is going in the direction the gravity wants to enhance. So for both growth rates, we positive for the base of the lithosphere, the instability will grow, and negative a decay rate, therefore, for the moho. They depend on the wavelength, as they do before. They depend on wave number. And by analogy with the Rayleigh-Taylor instability we talked about earlier, the largest positive or negative growth rate or decay rate they'll occur for wavelengths comparable to the thicknesses of the layers. Remember, it was a factor of 2 times the wavelength with maximum growth rate was twice the thickness of the layer in the simplest case we started with before. The same will apply here. And the growth or decay rates will scale with density difference. And therefore, the decay rate for the MOHO should exceed by several times the growth rate for the mantle lithosphere, because the density contrast at the MOHO is much greater than the density contrast at the lithosphere-asthenosphere boundary. So if we look at growth rates, again, non-dimensionalized here, versus wave number, they peak and they're positive for the growing case with mantle lithosphere sinking. And remember, this is done differently for some reason, but anyway, the maximum growth rate is 2.6 times the thickness of this mantle. Well, it's because the lithospheric thickness includes crust, so it's not 2.1, it's 2.6, but it's very similar. The decaying growth rate is much larger. It's negative because it's a decaying instability, but it's much larger because the density contrast at the MOHO is much larger than the density contrast at the MOHO, at the crust mantle boundary. And the wave number is larger, wavelength is shorter, because the crustal thickness is thinner than the thickness of the lithosphere. So what happens when the growing eigenfunction dominates? Obviously, the dense layer, the mantle lithosphere, this layer pulls the less dense layer, the crust, pulls this down. This is obvious. This is no surprise. But what happens when the decaying eigenfunction dominates? What happens when the MOHO, when the low density of the crust wants to pull the MOHO back up? Then the buoyant crust pulls the MOHO up with it and pulls the mantle lithosphere up as well. But in that case, then, where does the mantle lithosphere go down? Remember, we're shortening the mantle lithosphere. We're thickening the mantle lithosphere. So if we're not thickening here, it has to go down someplace else. And it goes down right next door in the adjacent place, because this is in the perturbation, in the fastest growing growth rate, this would be the wavelength that you would expect that perturbation. So in the case of a growing eigenfunction, it wins. You have a single downwelling. In the case of the decaying eigenfunction, then the MOHO is pulled up, the lithosphere thins in this area, the lithosphere goes down, and in fact, you get some additional crustal thickening in this adjacent region. And back to this picture, again, this was our theory, where what's plotted here is the density, the viscosity contrast. So high viscosity crust to the right, low viscosity crust to the left. And here, product of crustal thickness, in a sense, and crustal density defined as we have. So this is thicker crust, you have paired downwellings, and less dense crust, you have paired downwellings. And this dashed line is a better approximation than our theoretical curve. But we're looking at 3 orders of magnitude. We're happy with this, even though it's imperfect. So geodynamically, what does this mean? Well, paired downwellings and lithospheric thinning will occur beneath the zone of crustal shortening. They're favored by thick, buoyant, low viscosity crust. That's what the plot I just showed you was meant to say. Sorry, backwards. But this means if you have thick crust, that we're thick relative to what? Relative to the lithosphere. So paired downwellings will be favored by thin or hot mantle lithosphere, because hot mantle lithosphere is thin lithosphere. The crust is the same thickness, so the crust is relatively thick when the mantle lithosphere is thin. And that will come in when I introduce the Tian Shan. So initially, thin lithosphere, if shortened horizontally, will thicken because it's weak. That's the locus of thickening. But thin lithosphere may stay relatively thin because downwelling will occur on the flanks, and the weak regions can remain weak for a long time. So we'll look at the Tian Shan as an example. This is in Asia. So India's here, Tibetan Plateau. Tian Shan is this belt coming across. Earthquakes. There have been a number of magnitude 8 earthquakes in this region over the past 130 years. And GPS shows rapid shortening across here. GPS velocities across Tian Shan, it's fast, 20 millimeters a year. but there's not a lot of shortening in this region. In addition, there was sporadic volcanism from 120 million years ago to 25 million years ago. And therefore, the lithosphere was relatively warm. The upper mantle was warm, and so the lithosphere presumably was thin. And then we had this acceleration at 20 or 25, or 10 or 15 million years ago. Well, this is a distribution of seismograph stations laid out across the western Tian Shan in Kyrgyzstan and in Western China out in here. Here's a little blow up. And I'm going to show you results of tomography of different kinds. So here's a black and white map. Lake Issyk-Kul is a deep lake in the middle. This region is the same region as you're seeing over here. And this is P wave speeds getting down in the upper mantle, getting down below 7.5 kilometers per second. Very low P wave speeds in here, very low P wave speeds in the highest part of the Tian Shan. This is the highest part of the mountain range. So low speeds suggesting a hot region with high speeds in the surroundings on the two sides. Not that high, but suggesting a warmer environment. And then a tomogram across this profile coming through across this area. And what you see on this, the profile through it, so north is to the right, south is to the left, and you see high speeds. These are places that are more than 2% higher speed than the surroundings, high speeds on the flanks. High speeds on the flanks, low speeds underneath at shallow depths in the Tian Shan, in this area. And so what we argue, we have today, low P and S wave speeds suggest an upper mantle is still warm. And this early warmth both weakened the lithosphere, made the crust a large fraction of the lithosphere, so that we have a large ratio of crustal thickness to mantle lithosphere thickness, to total lithosphere thickness. And then the thickening of the crust and thinning of the mantle lithosphere subsequently occurred, and we wound up with that picture of a thin lithosphere under the Tian Shan and thick lithosphere, sinking lithosphere under the flanks. So I'm going to show you another example, the Alboran Sea between the Baetic Cordillera in southern Spain and the Rif Cordillera in northern Morocco over in here. And much evidence shows a low speed zone under the Alboran Sea. In fact, the crust is thin under the Alboran Sea. The black dots are showing earthquake locations. And so one has intermediate depth earthquakes under the Rif going down almost to 200 kilometers and quite deep under the Iberian side, and high speeds down underneath the Baetic Cordillera in southern Spain, southern Iberia over here. And so we would argue you have the same picture: sinking of cold material under the Baetic Cordillera, sinking of cold material under the Rif in here, and in between thinning of crust and of mantle lithosphere beneath the Alboran Sea in this area. And the same picture then applies to the Tian Shan as well. So, for a summary for the Alboran Sea, convergence and collision between Africa and Europe built a mountain range spanning the Baetic Cordillera and the Alboran Sea and the Rif in Morocco. Then, removal of mantle lithosphere in early Miocene time led to thinning of lithosphere, including the crust, beneath the Alboran Sea, while thrust faulting in the Baetic Cordillera and Rif continued, and the sinking of cold material beneath the Baetic Cordillera and the Rif continues today. Okay, I'm going to change directions again, or change topics. This is a compilation that we made years ago of the timing, the delay between thrust faulting and crustal thickening, and then normal faulting and extension within mountain ranges like Tibet. So the crustal thickening for a long time, now crustal extension. Basin and range, crustal thickening for a long time, later extension. And there's a delay. And the delay is what I'm going to focus on for the next few minutes. So a delay between lithospheric thickening and convective removal. And I'm going to argue that this is because of non-Newtonian viscosity. Remember this relationship, this simple relationship, that the strain rate varies as stress raised to some power n, where n is of order 3 to 3.5. Okay, I'm going to use this in a simple argument, a bit of mathematics, but not complicated. But remember, with Newtonian viscosity, the stress varies with twice the viscosity times the strain rate. This is writing it in words. But non-Newtonian viscosity, where it's dislocation creep, the stress varies as the strain rate to the 1/n power. This is the inverse of that relationship I had in the previous slide. Now, if one gets technical, one writes the stress tensor as some constant, viscosity coefficient, a property of the material, times the second invariant of the strain rate tensor raised to this quantity, this is a negative exponential, times the strain rate tensor. Fortunately, we are going to approximate that in a simple way, but it can be quite ugly. But just to show you, if you have a layer with Newtonian viscosity, you have exponential growth. This is now a layer, a segment where this part is thickened, this part is thinned, and then this repeats itself going off to infinity. The thickened area gets thicker and thicker and thicker, and the thinned area gets thinner and thinner and thinner, and this grows exponentially. If you have non-Newtonian viscosity, same pattern, you thicken this a little bit, you thin this a little bit, and then, of course, going off to infinity, this is thickened, this is thinned, this is thickened and thinned, and so forth, where you have symmetry. Here you have super exponential growth. Notice that the elapsed time, these are non-dimensionalized in different ways, of course, but the elapsed time you have a rather small perturbation at 0.81, and at 0.814, you've already jumped to this curve, and just slightly further, you've gone to this curve. So the growth is very, very rapid once it is growing. And in fact, with numerical calculations, if you imagine time and the downward displacement of the sinking blob or the downward speed of the sinking blob plotted this way, if it's exponential growth, it looks like this purple curve for this particular ratio of wavelength to thickness, or this one for that one. You get these blue and purple curves for exponential growth. With non-Newtonian viscosity, you have almost no growth and then catastrophic growth. And more spectacularly with downward speed. You don't see any hint of downward speed, and then all of a sudden, off it goes, very, very fast. Very, very rapid growth in here. Different wavelength to thickness ratio. It takes longer to start, but then again, very, very rapid growth, catastrophic growth. And so Newtonian viscosity implies exponential growth. Non-Newtonian viscosity implies super exponential growth, slow initial growth followed by catastrophic growth. And the question, can we understand this? And my strategy in all of this is to indicate that we can understand. If we can't understand, we shouldn't trust what we're doing. Too much numerical modeling is done without people understanding. So my father was a scientist. I briefly interrupt here. My father was a scientist, and there was a rare moment when I was a kid and I ignored him. Of course, all sons ignore all fathers, I think. At a moment when he thought I might be paying attention, and I was, an amazing time, he said, "Do you know what the most beautiful sight in the world is to an experimentalist?" And of course, I didn't have a clue, so I didn't know how to answer. And he answered, he was an experimental physicist. He said, a straight line of data points. So that is going to underlie what I go through next. Greg Hausman, with whom I worked and had the privilege of working, wonderful person, played a trick that allowed us to get straight lines, and I'm going to describe that. The basic equation for exponential growth is the rate of change depends upon the function itself. dw dt is proportional to w, and q is the growth rate. And this yields this exponential growth. W then grows exponentially. And q, of course, depends on density, gravity, thickness, and viscosity. Viscosity with Newtonian viscosity has this relationship. But for non-Newtonian viscosity, we have this very ugly relationship where we have a coefficient like a viscosity times the second invariant of the strain rate tensor times the strain rate tensor itself. And what we're going to do is substitute an effective viscosity, just take all of that and give it a number and plug it in. So we define the effective viscosity as a half B, second invariant raised to this power, this quantity in here divided by 2. That's our effective viscosity. But then we need to approximate the second invariant. And let's just say it's W, the downward speed of the sinking blob. That's a speed. divided by the thickness of the layer, H. So the ratio of those is a strain rate, and we're just substituting that quantity in for this. This is a very complicated number. This is obviously simple. And when we do this, some beautiful simplicity comes out of this. So we're saying the effective growth rate in here is this with an effective viscosity. We change Q prime to a C in here. But again, there's our density difference, there's our gravity, there's our thickness, there's our B as before. But now W, we've plugged this into this relationship, and we have W in this growth rate, W in here, and it's multiplied by that W up there. So when we do that, and we have this simple expression, but our new definition of the growth rate, we have dW dt varies as W to a power. This is very easy to integrate. We can integrate that, and what we wind up with this, some very ugly stuff, but these are just constants. And notice that when T equals TB, TB is a constant of integration, this quantity is 0. Well, this is not 0. This is not infinite. This is a negative number, but this has been a negative number. This must, for this quantity to be 0, this must be infinite. In other words, the downward speed is infinitely fast. Of course, we never get that. This is mathematics. But the point is, this defines a quantity, a blow-up time. Now, we can take this and go further. We can say, well, W is the rate at which the bottom of the blob sinks. We can do a bunch of mathematics. This is too fast for you to follow. I don't expect you to. But what you get is that the downward position raised to the 1 minus nth power varies with time, just as the downward speed to another negative power varies with time. And we get an estimate of what this constant is, this time. This is simply the value when T is equal to T0. When we start, T equals 0, T equals 0, we start everything, then Z0 would be the initial condition. In a sense, we have everything we need to solve for speeds and distances if we're given initial conditions. And so we plot not W versus time, but W to the 1 over n minus 1. This is a negative power. And Z to the 1 minus n, again, a negative power versus time. And there we get straight lines. This is, my father died long before we did this, but he would have been very proud of this. And I argue if we could predict data so that it falls on a straight line, we understand. This is a key to understanding. So what we're finding is this relationship, but not only that, we're getting a value for the blow-up time. So just to go back to this plot, if it's exponential growth, it looks like these purple or blue lines, but with power law, we have slow initial growth, which hides an unstable state. We don't see it. You don't see at all. The box is too big to show you the downward speed raised to the downward speed. It's too small to show you the downward speed. And the displacement is very small here, only starts to grow right near the blow-up time. And it blows up. Obviously, it's going off to infinity at this time. So then we have catastrophic growth later, long after the perturbed state was created. So if we look at a place like Tibet, where we had collision at 45 million years ago, steady penetration of India into the rest of Asia, Eurasia, since collision. Now we have normal faulting, east-west extension, and crustal thinning. Some change must have occurred. The onset of normal faulting is 15 million years ago. We can ask the question, well, why was there this long delay between collision back at this time and crustal thinning beginning at this time? And I would answer, it's nonlinear viscosity. It's because the growth of the instability just took a long time to occur. Now we can go further. We have this instability time, the elapsed time for a perturbed thickness to blow up, to go off to infinity. And it's an ugly function, but we know all these numbers in principle. N is that power, it's 3 or 3.5. B is a number, actually, I'm going to turn this around and infer. C is a number we get from numerical experiments, gravity, density difference, thickness of the lithosphere over here. This is our initial perturbation. This just comes from doing integrating in calculus. It's nothing complicated. So if we knew this and we knew all of this, we could predict that time, but we can turn this around. As I said, we've estimated C from numerical calculations. So I'm going to put some numbers in for these various parameters. And this is the target. We're actually going to turn this around, use an estimate, a geologic estimate of that to estimate B. And so this is that same formula. And remember that B, and from laboratory experiments, depends upon temperature by an Arrhenius law like this. So if we plot temperature in kelvins over here, and the log of B, for dry olivine, B is larger than it is for wet olivine over here, and eclogite, there have been measurements that they follow this form. Unfortunately, this first case I'm going to show you is a little bit more complicated because we have to worry about Peierls creep. And so these blue lines are meant to be approximations to this equation, but using Peierls creep. And so one has a complicated rule defined by those blue lines. I just ask you to trust me that we've done this safely. If we go back to the Sierra Nevada, we have these blobs sinking, and we know pretty well that the deblobbing time is about 7 million years. This has been sinking for only about 7 million years. We know this from the geologic history, from volcanic rock, and from how far down it's gone, in fact. So we can put a 7 million years in, and when we do, we get a bound on this value of B. This is the value of B, and it's between, these units won't mean anything to you in Pascal seconds to the 1/3 or Pascal seconds to the 1/3.5. They don't mean anything to you, but these are the range of values of B that we get back on that plot of temperature that we had before. And when we can then come back in and say, well, where can these be? And the temperature at the MOHO could be as cold as 550 to 600 degrees, to 600 kelvins. We're in this very cold region. We can turn this around and solve for B. And let me do this with a simpler example from the Eastern Cordillera of Bolivia, down in here, where really nice work by Carmi Garzioni has shown that this region rose rather abruptly. There were low elevations, around 1,000 meters or lower, until 10 million years ago. By 5 million years, this had risen to its current elevation. In fact, 6 million years here and 9 million years there. So that the blow-up time is only 3 million years. We can be quite confident of this, and we're quite confident that you've removed mantle lithosphere from here. So if you put this value in with guesses for, well, we know gravity, but the density, the thickness of the lithosphere, the initial perturbation, and with uncertainties in these, we wind up with a range of values of B. Again, these numbers don't mean anything to you, but I plot them here, show you them against temperature from laboratory experiments. Again, dry olivine, wet olivine down here, and eclogite. And again, we come in and we can predict the temperature down here at the bottom of the mantle lithosphere, at the bottom of the lithosphere, within the lithosphere, sorry, the temperature within the lithosphere at the time when the blob began to sink. Okay, one last question. Do we see sinking, stretching blobs of mantle lithosphere today? And if so, where? In other words, do we see this pattern happening? And the work I'm going to describe is by Lorenzi and Hausmann. They made these calculations, but they also brought data to bear. And this is from the Carpathians in Romania. So this is the Black Sea over here. This is Italy, the Alps, the eastern edge of the Alps. And these are tomograms. So if we look on this plot across here, across the Carpathians up here, red is low speed and hence low temperature. I neglected to put a scale in here, but this means it's hot. This line going along here is this plot, and you see it's low speed along most of this, but then in here you have high speed. The blue is high speed, and you have earthquakes. These red dots are showing you earthquakes. This is just this corner of the region, a blow up of this area in here, showing these earthquakes. These earthquakes are in a vertical zone going down to 200 kilometers. Almost all of these earthquakes show thrust faulting, but more importantly, they show a vertical T-axis. So you have vertical extension and horizontal compression for all of these. And one more cross-section through here. Again, it's low speed under the earthquakes, high speed under the earthquakes, high speed under the earthquakes, but elsewhere it's low speed in the upper mantle. They argue, and I follow them, that this is a sinking blob of mantle lithosphere going down in this area. And when they do their numerical calculations, the blue is showing the horizontal, this is horizontal extension rate, and hence it's positive, meaning I'm sorry, I've mixed these. No, I haven't mixed. The vertical extension rate is large and you're stretching in here. The horizontal extension rate is negative because you're compressing in this area. So this blob is sinking and being compressed horizontally. This is the image that they have of this region. And there's one other place where we think this is going on. I think I showed you this picture a long time ago of intermediate depth earthquakes showing you down dip extension with black, down dip compression with red. These are all island arcs, subduction zones. There are only two that are not. The Hindu Kush in here, and what we wrote is Romania. This would be the Carpathians in Romania over here. All of these are subduction zones. And what's important is that these two regions, they're different because they're under continents, but they're also different because the strain rates estimated from sums of seismic moment tensors are 10 times larger than in any of these. These are stretching vertically 10 times faster than any of these other places are stretching or being compressed. So it's a very different situation where you have a downgoing slab of cold lithosphere plunging underneath Middle America, for example, than you have here, where you have a blob of material stretching rapidly, 10 times faster than the stretching in this case. So to summarize, convective removal of mantle lithosphere can account for Barrovian metamorphism. Because diffusion of heat is much slower than advective heat transfer, Rayleigh-Taylor instability offers a method for quantifying convective removal of mantle lithosphere, convective removal up here. We can do that because we can ignore diffusion of heat. For sensible density anomalies and viscosities, Rayleigh-Taylor instability is fast. So you can remove this in a few million years, remove mantle lithosphere quickly. This is possible. When the overlying crust is thickened, Rayleigh-Taylor instability can lead to lithospheric thinning where the crust has been thickened. And this is because of this paired downwellings that we can get because of the nature of the instability where you have a crust and you force it. Non-Newtonian viscosity can lead to super exponential growth, slow initial growth followed by catastrophic growth, where everything is very fast. And finally, sums of seismic moments of intracontinental intermediate depth earthquakes suggest ongoing removal of mantle lithosphere beneath the Carpathians and the Hindu Kush. And there surely are other places undergoing removal of mantle lithosphere, but we can't study them as well or as easily because they don't have earthquakes happening there. And so I leave you with this picture, which is meant to be the cartoon that justifies what I've been saying. And I did not use the full hour. Back to you, Hector.
Okay, thank you very much, Peter. There are some questions. In the Rayleigh-Taylor instability, what controls the generation of large blob rather than a constant dripping scenario?
Sorry, what controls?
The generation of a large blob rather than a constant dripping scenario?
That's a good question. My guess is that there is constant dripping in general, but very slow. And what accelerates the Rayleigh-Taylor instability in mountain belts is you thicken the mantle lithosphere. It's this thickening process over here where you force a thick mantle lithosphere. You force not just a thick mantle lithosphere, but a thickened area. And so this grows very rapidly because the perturbation is large. Whereas if you had only a small perturbation to the surface here, as you do under Shields and under other regions, you would have very slow growth and although maybe steady a steady growth, steady pattern, you wouldn't get the big removal of mantle lithosphere. It's the thickening that's most important. The thickening imposed by crustal shortening and lithospheric shortening.
Okay, thanks. The other one. How close to the trench in a convergent margin a Rayleigh-Taylor instability could take place?
Oh, that's a hard question. Yes. I mean, obviously, right where you're subducting, you have cold material already there. And so you wouldn't expect this to happen. And in the case of the Bolivian Andes, we don't know. I don't think we can be sure, but we imagine that the instability grew on the eastern side of the Altiplano, not the western side. But we don't know that. Tomography can be used to try to draw inferences. I don't have a lot of confidence in what people say, but I would predict that in a place, in a real island arc, like the Aleutians or the Marianas, you wouldn't see this at all. But where you can thicken both crust and mantle lithosphere back inland, as you can in the Andes, then I would expect this phenomenon could happen. And for instance, I can imagine it might, I don't think it has, but I could imagine it might happen under the Eastern Cordillera of Colombia. I can imagine that it might happen under Japan, on the west side of Japan, and certainly along the central Andes of South America, no problem. There is a place where this seems to be happening on the west side of the North Island of New Zealand. So the North Island of New Zealand, there's a subduction zone, but farther west, there seems to be a place where there's a drip going down, a drip without earthquakes in it. But I think the New Zealanders have done a good job. So it can happen. In that case, it's only 100 kilometers from the, or approximately 100 kilometers from the volcanoes associated with the island arc. So it's conceivable it would be close in that sense. I must admit, I haven't thought hard about this question, so my answer I might change my mind tomorrow.
Okay, there is another one. Is there a relationship, or what is the role of the Rayleigh-Taylor instability in the viscoelastic relaxation?
Well, that's a good question too. We actually studied, I was part of a study many years ago where we did Rayleigh-Taylor instability with a viscoelastic medium, and the elasticity played a role, so that the growth rate was a little bit different. We didn't examine non-Newtonian viscoelastic. We examined only Newtonian viscous and elastic, but it meant that the growth rate stabilized, as I recall. I confess I've forgotten the results that we got, but I think the main answer is it did not retard or inhibit the process. It just changed its growth a little bit. But the questioner may be asking about what's the role with viscoelastic processes associated with earthquakes, and there I don't think it matters, because we're talking about something that takes a few million years to evolve, not an earthquake cycle.
Okay, Peter, there are no more questions so far. Thank you very much.
And if there are, you can email me them and I can answer them.
Okay.
Yep.
Muchas gracias a todos por su atención. Nos veremos el próximo martes. Buena tarde.